Okay, so in physics 20, obviously we have to talk about acceleration. Acceleration is part of kinematics, it's part of projectile motion, it is part of dynamics, Newton's second law, it's part of circular motion, okay? It's part of simple harmonic motion. The concept of acceleration is crucial to basically all things physics, right? Now, we already know what acceleration is. We talked about it in Science 10, okay? We did a lab about it, all that kind of stuff. So the first little bit of this will be a review, but we're going to add to it. Last year in Science 10, you would have had one and only one acceleration formula, and that would have been this one. A equals VF, okay, minus VI over t. Change in velocity over change in time, okay? Which, incidentally, is y equals mx plus b for a velocity versus time graph. We're going to look at that, but we're also going to add 4 more formulas to the list. Okay? If you look at your data sheets, okay, there are 5 acceleration formulas in the acceleration part, okay, of that, of the kinematics part of your formula sheet. Okay? We're going to go over all of them. It's just algebra. Okay? We're going to talk about where those formulas come from and why they're useful, but in the end, all you're going to be asked to do with them is use them to solve problems. So do algebra, solve for A, or solve for VF, or what have you. Okay? So, understand what accelerated motion is. Well, very simply, acceleration is any change in, not movement, too general, velocity, right? Any change in velocity, right? Not speed, velocity, any change in velocity. Does that mean you can't put speed into this formula? Absolutely not. You can totally put final speed and initial speed into that formula, but it's set up as a vector, okay? And that also means then that acceleration is a vector quantity, so direction matters. All right, so we're going to look at the relationship between change in velocity, distance, time, and acceleration. That's a little bit of graph stuff. And then the formulas, okay, be able to solve accelerated motion problems. Okay, so whenever the velocity of an object is changing, acceleration is going on. That's why I showed you that little meme the other day, okay, that showed the driver's side view of a car, and everything was labeled accelerator. Steering wheel, the brake, and the accelerator pedal, okay? Because they all cause changes in velocity, even turning, right? You're changing your direction. That's part of velocity. So even making a turn requires an acceleration, okay? Ask anyone who ended up in the pond on that corner over there because they tried to take it too fast and their tires would not provide the necessary change in velocity, direction, around that corner. Every year somebody ends up in that pond and they become the butt of my jokes about unbanked corners and things like that. So don't be the person who ends up the butt of my jokes, because somebody does every year. Okay? Don't go in that pond. Go slow. All right, so average acceleration or uniform acceleration would be better, okay, is best illustrated by a plane during takeoff, not a car accelerating away from a stoplight, okay? What's the difference between a plane accelerating for a takeoff and a car accelerating away from a light?
The car starts off slow and gradually goes up.
Well, the plane will have, it probably would have a steeper curve for sure, but it also does that. But what's the difference? You have to change something, or maybe your car does it automatically, that in the car that you don't in a plane. Gears. Okay? I don't know if you guys have noticed this, but when you first hit the gas pedal, that's when you get the most acceleration. First gear provides the highest rate of acceleration, okay, versus 6th gear or 8th or however many gears your transmission has. Maybe you have a continuously variable one that just doesn't really have gears. Okay? But cars that have a transmission, okay, are going to not accelerate uniformly. Okay? Their velocity versus time graph is not going to be a nice diagonal line like a plane. Okay? Because a plane doesn't switch gears. You just push the throttle forward and off it goes. Okay? It's going to accelerate much more uniformly. In a car, because you have to switch gears, your graph actually kind of does this. The higher the gear, the less acceleration can be produced. If you've ever had to pass somebody on a 2-lane road, right, and you mash the gas pedal down, your car probably downshifts 2 or even 3 gears in order to give you the acceleration that is required in order to get around quickly. Right? Does anyone here drive a manual? Stick shift. It's less and less every year. That's the first time I've had nobody. Okay? But like back in the day when more cars were a manual, if you wanted to pass somebody on the highway, you didn't leave the car in 6th. Okay? Otherwise you were going to die because you weren't going to get enough acceleration to get out and around. Okay? You would probably pop that thing from like 6th to 4th or 5th to 3rd, okay, in order to get the acceleration that you require. Your automatic transmission does that for you when you mash the gas. Okay? Everybody with me? Because you don't want to be using this part of the graph to pass somebody. You want to use this part of the graph to pass somebody. Yeah. Okay? Making sense? All right, so we'll start out with the first formula here, okay? The one that we knew from last year, that acceleration, which is a vector quantity, okay, is final velocity minus initial velocity divided by time, okay? Remember that that comes from a velocity versus time graph, okay, where y would also be your final velocity, b, okay, b would be your initial velocity, or how fast you were going at time 0, okay, and then x would be time. Okay? You're finding the slope of that line when you use that formula. Okay? You're taking the change in velocity, the change in y minus b, and you're dividing it by the change in time, or the run of x. Making sense? Okay, so kind of easy example here, right? Suppose I got this plane, and at time 0, it is at rest. Okay, that's a term we have to know. It comes up a lot. If something is at rest, it isn't moving. So if something starts from rest, its initial velocity is 0. What if it comes to rest? Yeah, its final velocity would be 0 if it comes to rest or came to rest. Okay, just so you know, the term rest means not moving. So something either starts from rest, VI is 0, comes to rest, okay, VF is 0. All right. It accelerates for 29 seconds, okay, and attains a velocity of positive 72.2, where the plus sign indicates right. Okay? All right, so my givens in this question are, I know VI, I know VF, and I'm going to put up here that positive equals right. Okay? And I know the time. The time is 29 seconds. All right. Here's where writing down your givens is important. The question wants me to calculate acceleration. My formula sheet has a ton of formulas on it that have A in them. Okay? Because acceleration is an important part of a lot of the things we do. Does writing down my givens help me figure out which formula I should use? Yeah. There's only one formula on your sheet that has A, VF, VI, and T in it. All right? So you got to play a little game of I got to match what I have with what formula fits with it. Okay? So that means I'll be using the one I learned last year in Science 10. A equals VF minus VI over T. Lucky for me, the question wants acceleration. Formula's already set up for that, so I don't even have to do any algebra. I just need to plug numbers in. Okay, so A equals 72.2 minus 0, okay, divided by 29 seconds. Now, on your calculator, with a formula like this, it is important that you make sure the top gets done before you divide by the bottom. I mean, in this case, because one of the numbers is 0, it doesn't matter, okay? But if it's not, you have to make sure that the top is done before you divide by the bottom. You can't just punch it in like this and go, well, in this case, you could 72.2 minus 0, okay, and then go divide it by 29. If you do that, what's your calculator going to do? It's going to do 0 divided by 29. And then it's going to subtract that. Actually, it won't give you the right answer. You'll subtract that. You'll subtract 0 from 72.2. Okay? Versus what we want it to do. Okay? So that gives you 72.2. Okay? We want it to go 72.2 minus 0 divided by 29. Okay? That gives me a much different answer. Right? I have to ensure that this is done in the way I want it done, not the way my calculator was programmed to do it. So this is telling me that 2, how many significant digits here? 2. My time was 29 seconds. That has 2 significant digits. Okay, so my answer needs to be 2.5. Right. What are the units for acceleration? Meters per second squared. I would also accept if you went meters per second. It's the same thing. Okay, we just generally write it as meters per second squared. Okay, and the reason for that is kind of what happens if you're doing fractions. So if I have meters per second and I'm dividing that by seconds, that's seconds over 1. Okay, if I want to divide fractions, what do I do? What do I do with the second one? I reciprocate and then multiply. Okay, so instead of dividing by seconds over 1, I'm actually multiplying by 1 over seconds. Well, m times 1 is meters. What's seconds times seconds? Seconds squared. Okay, either way is correct. Okay, we just generally say meters per second squared. Write it that way. Okay, things like that. All right, so it's telling me that this plane, on average, goes 2.5 meters per second faster every second. All right, is that fast? Probably doesn't seem like that big a number, but you would feel that. Okay, if you were on the plane, you would feel pushed back into your seat. Okay, because that's how you would feel. Literally, it's actually the seat pushing on you, accelerating you forward with the plane, but we'll talk about that in Unit 2. Okay, but you would feel a little bit heavier than normal. And if you're just sitting in a car that's not moving, you don't feel anything. But if the person mashes the gas, you feel pushed into your seat. Okay, same idea. Everybody all right with that? Okay. These are our other formulas, our new ones that are going to be on your formula sheet. Okay? They all involve displacement. Okay? And even oddly enough, one of them, which involves acceleration, doesn't even have acceleration as a variable. And that would be the last one. Right? All the others do. So, what I want to show you here is how these formulas work. Okay? In particular, the first two. We had a question today on our quiz that wanted us to calculate the displacement from a velocity versus time graph. Okay? So I'm just going to give you an example graph here. Let's say my graph looked like that. Okay? Velocity versus time. So meters per second and seconds. If I wanted to calculate the displacement of that object, would I calculate the area under the line? Right? That's how we've been taught to do it. Okay, so does that mean that I've got a rectangle and a triangle? Right? That would be the two shapes that are between the line and the x-axis. Okay. Now, this spot right here, this would be B, right? And B represents initial velocity. So if I multiply my initial velocity by time, did I just go base times height for this rectangle? Absolutely. Okay, so this calculates the area of the box. And this calculates the area of the triangle. Okay, so kind of in looking at that, we've got the slope of this line here, right? The acceleration, that would be the acceleration, okay? And if I did half of that value, okay, I would get like basically the height of this triangle, and then I would be multiplying that by the time squared. Now I'm gonna kind of illustrate that a little bit differently here, but suffice it to say, this is 1/2 AT squared. Your rate of change of velocity, okay, multiplied by the time, and then if you take the half of that, because you have to use the average, okay, you'll get that area of that triangle. Okay, so these two parts calculate the displacement. Okay, now this one's a little different. Instead of starting with VI, it starts with VF, and instead of adding, it subtracts. So would this value up here be VF? So if I go VF times T, do I calculate this whole box? I do. And then I subtract this. Well, is this triangle and this triangle the same triangle? Okay, so if I subtract this triangle, am I left with this? They're calculating the same thing. They're calculating the area under the line from two different perspectives. One from looking at it from the beginning, the other looking at it as though it's from the end. Okay, but in the end, they both calculate that here. Everybody with me on that? Okay. So if you have a graph like this, which maybe we will on our lab on Thursday, okay, that might come in handy. Okay, VF squared equals VI squared plus 2AD. Not going to talk about a graph for that one, but this one comes up a lot when we're talking about projectile motion, so an object flying through the air. Okay, what variable does it not have? Time. Okay, this one allows you to manipulate and find displacement, acceleration, or one of the two velocities without knowing how long the object is accelerating for. Okay, that can come in pretty handy in a situation like if I threw a ball up into the air, being able to calculate how high it would go without knowing how long it would be in the air for. Okay, be able to use the formula for that kind of situation. Okay, and then our last one here, okay, we don't use this one very often, okay, because the acceleration has to be uniform for it to work, okay, and obviously it doesn't even have acceleration in it, but it does involve change in velocity. That part is in the formula, right? There's the indication that the velocities are changing. But if I asked you, take the final velocity and add the initial velocity and then divide by 2, what is that kind of like calculating? Nope. Close. If I ask you to add two things together and divide by 2, you're essentially calculating their average. Right? If I ask you to add 3 things together and divide by 3, you'd be calculating their average. Agreed? So if I take the final velocity, add the initial velocity, then divide by 2, is that finding the height of the triangle? Right? Kind of. It's calculating the average velocity. Well, if this whole thing here is average velocity, and I'm just multiplying that by time, well, no wonder it calculates displacement. We've seen that formula before, okay? All it does is just take into account that the velocity wasn't constant. It does have to be uniform acceleration for it to work. And you'll see questions, they'll say, an object accelerates uniformly from this. Then you know that formula is in play. Okay? If it doesn't say that, that formula is not in there. Okay. Well, let's go through. What we'll do here, guys, is I'm going to have you write down an example. We'll go through it together. And then I'll have you do a few practice questions with each formula. Okay, and then we'll go through them together and solve. So you see each formula used, each formula manipulated. All right, let's have a look at this one here. You guys probably already figured it out, but let's go through it anyway. So we have this car with an initial velocity of 10 meters per second east. Okay, always write down your givens. They told me initial velocity, okay, 10.0 meters per second east. It accelerates at 3.0 meters per second squared east. All right, so they gave me acceleration. Okay, how long will it take the car? So how long? What am I solving for if they want how long? Time. How long will it take the car to acquire a final velocity of 25.0 meters per second east? All right, so they gave me VF. Now, I do want to caution you. I am not going to give you questions that explicit. Okay, the initial velocity is this much, the final velocity is this much. There's going to be a story to read, a boring story, okay, that you have to get everything out of. Okay, I'm not going to outright say, here's everything. Right? Then I might as well just write down the givens for you. Right? So know that as we go along, the stories will become ever more complex and boring. Okay? All right, so we're trying to solve for t. I have VI, A, and VF. What's a good formula to use here? Yeah, my good old Science 10 one, right? The one from last year. A equals VF minus VI over T. But it's not set up for T. I have to move it around. Okay? So, if I want to manipulate this formula to get T by itself, what should I do with T? Multiply it over to the other side. Okay, so I multiply both sides by T. What do I do with A? Divide. All right, so now I've done my manipulation. Okay, like incidentally, if you were doing this on a quiz or a test, I'd give you a mark for the givens. I'd give you a mark for picking the correct formula. Okay, and I'd give you a mark for your manipulation and or plugging in of numbers. Okay, so what we would have now is T equals 25 minus 10 divided by 3, right? 25 meters per second, 10 meters per second, 3 meters per second squared. All right, so 15 divided by 3, this should take 5.0 seconds. All right, and you would get a mark for that. So this would be a 4, most likely 4-mark question, maybe a 5 if I was saying, oh, I'll give you one for this and one for that. Okay? Questions on that one? Okay, so I can't stress how important algebra skills are in physics. Okay, I mean, basically everything we do involves manipulating equations to solve for something else. Okay, so something to practice or come in and get help on for sure if it's giving you trouble. All right, I would like you guys to try those 2 questions there. Okay, they're using the same formula. However, something you need to watch out for. In question number 2, they give you meters per second squared, they give you seconds, and then they give you kilometers per hour. I would say probably should convert the kilometers per hour to meters per second. So to do that, convert the kilometers to meters, okay, and convert the hours to seconds. Okay, there's 3,600 seconds in an hour. Okay? Or you could do this. I'll show you a little shortcut. Okay, if I want to convert kilometers per hour to meters per second, I would first have to multiply the kilometers by 1,000. Right? There's 1,000 meters in 1 kilometer. Okay, if I do that, kilometers will cancel off. If I want to convert hours to seconds, in 1 hour, there are 3,600 seconds. Okay, so basically I'm taking whatever I had in kilometers per hour, multiplying it by 1,000, and then dividing by 3,600. Or, quick trick, okay, 1,000 over 3,600 can be reduced to 1 1 over 3.6. So could you just divide by 3.6? A little trick you're going to use a lot in physics. If I want to go from kilometers per hour to meters per second, I would divide by 3.6. Okay? If I want to go from meters per second to kilometers per hour, I would multiply by 3.6. 3.6 is the maximum. Okay?
You have to show that one.
No, I'm not worried about whether you show that work or not. That's just something you have to do to make the units match. Units always have to match. Okay, I'll give you guys a couple minutes. Number 1 works just like the example we did, right? This motorcycle has an initial velocity of 6 meters per second east. So VI for that one is 6.0 meters per second east, okay? And it accelerates at 4 meters per second east. Okay? So they gave us the acceleration, meters per second squared, east, so it is accelerating in the same direction that it's going, so it's going to go faster. Okay, how long will it take, looking for time, to reach a velocity of 36 meters per second east? Whoops, not 3.6, 36.0 meters per second east. All right, So I've got this information I need to solve for t. This would be the formula I'm going to use, Vf minus Vi over t. I'm going to multiply both sides by t. I'm going to divide both sides by a. Right? I'm manipulating and solving for t now. Plug in my numbers. 36 minus 6 divided by 4. Okay? So when I do that, I should get 7.5 seconds. Okay, 2 significant digits, right? The 6.0 and the 4.0 both only had 2 significant digits, so that's all my answer can have. Any questions on the first one? Okay, how many people have done the second? Okay, are we stuck on the conversions? Or we just need a little bit more time? I'll give you 2 more minutes, then we're going to go through. Okay, so in number 2, we have an elk moving at 20 kilometers per hour. That would be its initial velocity. But I need to convert that to meters per second. So I take that 20 kilometers per hour, divide by 3.6. All right, so I got 5.5. But I'm going to leave all the decimals in my calculator. I'm repeating up here, okay, but I'm leaving all the decimals in my calculator, which is what you should always do as well. Okay, it then accelerates at 1.5 meters per second north, so it's still going to be going faster. It's accelerating in the same direction that it's already moving. Okay, and it does that for 9.3 seconds. Okay, so 9.3 seconds, and we are looking at a maximum. We're looking for the maximum velocity. All right, so different manipulation here. I still want to use this formula, A equals Vf minus Vi over t, but now I want to solve for Vf. What should I move first? Time. Remember the 3 rules of algebra, right? If I want to move something, I do the opposite. What I do to one side, I do to the other. And the 3rd rule that you hardly ever used in Science 10 is move what's not attached first. So whatever I'm looking for, I move what isn't attached to it first. T is not attached to Vf. It's below it. Vi is attached to Vf. All right, so I'm going to multiply both sides by t. Okay, I'm going to multiply both sides by t, and then I'm going to add Vi over to the other side. Okay, so if I'm talking my way through this, okay, before I move to Vi, this calculated the change in velocity, right? T times A is equal to Vf minus Vi. So T times A calculates the change in velocity. So if I add Vi to both sides, I'm saying, here's how fast I was going at the beginning. If I add how much I change it by, that should tell me how fast I'm going at the end. Okay, that makes sense if I talk it through like that. Okay, now I just plug in my numbers. 5.5 plus 9.3 times 1.5. Okay, so I'm going to take that number there that I already have. I'm going to add it to 9.3 times 1.5. This one I can just write all in a row because I want it to do the multiplication first. Okay, that gives me 19.5, but that's in meters per second. Now I want it to go back to kilometers per hour. So I multiply by 3.6 to 2 significant digits. I've got 70 kilometers per hour. Okay, everybody all right with that? Yeah, elk can run fast. And if you've ever seen them run, figure they got to outrun a grizzly bear. They can move really fast for something so big and scary. Maybe that's what makes them scary. Okay, let's have a look at the other manipulation. There's one manipulation of this formula we didn't have to do. What if I needed to manipulate that for VI? What should I move first? Still time, yeah, it's not attached, so I would still multiply both sides by time. Okay? Now what?
VI.
Yeah, I would actually want to move VI. You don't have to do it this way, but I do. Okay? I know you're probably thinking, well, if you move VI over there, you're not solving for it. That seems kind of dumb. Okay, but watch. If I move VF over, okay, I would be subtracting VF. So I would have T times A minus VF. What does that solve for? Negative VI. So the reason I don't do it this way is I don't have very good memory. And I'll forget that I solved for negative VI, and I'll get the vector wrong. Okay, when I go back to convert this from east and west, whatever, I'll have the wrong vector on, the opposite one in fact. I don't want to do it that way. Okay, if you want to do it that way and you can remember, I'm totally okay with that. Okay, I'm just showing you the way I would do it. I would add VI over to this side. Now, VI is positive. And then I just subtract T times A over to this side. Now I'm solving for positive VI. Okay, now let me talk you through why this formula works. T times A, remember, calculates the change in velocity. So if I take my final velocity and subtract how much I changed it by, that should tell me how fast I was going at the beginning. All right. I want you to copy that one down. See if you can figure out what formula goes with that one. So we have a cattle train traveling west at 16 meters per second. That sounds like the beginning of a boring story. So I'm going to say that that is 16.0 meters per second. It's west. I'm making that the start of the story, VI. Okay? It is brought to rest. What's VF? 0. Find the displacement of the cattle train. So now I'm looking for D. While it is coming to a stop. Assume uniform acceleration. All right, sorry, the thing I missed there was the 8 seconds. Okay, so they outright say that it took 8 seconds. I have time, I have VF, I have VI, and they say uniform acceleration. Okay, which of the formulas that we had on that screen would fit here? Because it doesn't have acceleration in it, does it? Okay, I'm thinking it's probably this one. Okay, I have VI, I have VF, I have time. I don't have acceleration, but I know the velocity is changing. Okay, this is the only one I can use here. And remember I said, anytime that formula is in play, they are going to explicitly state that the acceleration is uniform. Okay, do I have to manipulate here? No, okay, I can just plug in numbers. So VF, 0, okay, VI, 16, right? And I'm gonna say that that's positive just because that was the only direction I was given. So positive would be west. Okay, divide it by 2 in brackets, and then multiply that by 8 seconds. All right, well, last time I checked, 16 over 2 is 8. All right, and 8 times 8 is 64. So, in stopping, this will travel 64 meters west. Okay. Everybody okay with that? All right, let's look at some possible manipulations of that formula. Okay, let's say I want to solve for t. What do I move?
Divide VF plus VI. Divide that over to the other side.
Yep. Divide the whole bracket over to the other side. Remember, in order of operations, do I always do what's in brackets first? Okay, so this is really just a number, right? It's like x. I can just move the whole thing because I would do it before I multiplied it by t anyway. Right? So there's absolutely nothing wrong with dividing the whole bracket over to the other side. In the end, it represents average velocity. Okay? So VF plus VI over 2 just comes over as an entire term. That equals t. D over V, right? When we use V equals D over T, we're solving for T, it's D over V. All right, what if I wanted to solve for either one of the V's?
Do you have to times 1 in it to get rid of the bracket?
No, I'd want to move something first.
So T.
Yeah, move t first, right? If I divide both sides by t, I'm going to have, gee, surprise, surprise, d over t equals average velocity. Right? Now, I don't need the brackets anymore, do I? T is gone, so brackets are unnecessary. I want to isolate VF. What do I do with the 2? Multiply. Okay? And then what do I do with the other V? Well, they're both going to be subtract, right? Because here I'm adding. Right? So I just subtract whichever V I'm not looking for. Right? Move it over to the other side. Okay? You can. Now, something I would caution you about, like I'm going to go, on each of these, I'm going through all the different manipulations. Okay? What I sometimes see people do is they copy down all the manipulations. You're not going to have access to those on a test. Okay? You have to be able to manipulate these on your own. I'll give you all of the formulas, just like what's on your formula sheet, but I won't give you all the manipulations. Okay? You can't just write down all the manipulations on your formula sheet and think that's okay, because it won't be. You don't get your formula sheet on a test. I give you a fresh one. Okay? So you have to be able to do the algebra. Okay. Try those two. I will caution you on number 2. Direction is important. Okay, let's have a look at these ones. Oh, I left that running the whole time. Nice. Okay, so hound is running at a velocity of 16 meters per second south. All right, so VI is 16 meters per second south. Okay, slows down uniformly to a velocity of 4 meters per second south. Okay, in 4 seconds. Okay, what's the displacement of the hound during this time? All right, so only formula I have that has those things in it is the one we just talked about. Okay, D equals VF plus VI over 2, okay, times T. So if I'm looking for D, I don't have to do anything, just plug in my numbers here. So that'll be 16 plus 4, actually the other way around, but it doesn't matter because we're adding, okay, divided by 2, okay, so 10 times 40, or 10 times 4 is going to give me 40 meters, and because it's all south, he ends up south. Everybody all right with that? Okay. How many people have done number 2? Okay. So in number 2, we got a ball moves up a hill with an initial velocity of 3 meters per second. So I'm just going to do this and go up, down. Okay, so VI is going to be 3 meters per second. Up hill. Okay, VF, okay, is going to be 9 meters per second down the hill. And that, we're looking for the displacement if that takes 4 seconds. Okay, now, something I will never do that is in this question. I will never give you a number as a word. How many significant digits does FOUR have? Hell if I know, right? Like, I mean, if they don't tell me how they measured it, how am I supposed to know? Okay, so now I can't do significant digits with this question because I have no idea how accurate they measured that. Maybe they just went 1 Mississippi, 2 Mississippi, and that's how they measured 4 seconds. Okay, but I don't know whether they did that or if they had a laser timer. Like, I don't know. And so now I can't do significant digits, which is why this question is terrible. Okay, because you should never give a number as a word. Okay, so don't ever give me a number as a word either. All right, so I've got that. I'm looking for D. Once again, I don't have to manipulate, but when I go into this formula, VF plus VI over 2, okay, times T, I've got to make sure down the hill is represented with a negative. Okay, so negative 9 plus 3, okay, divided by 2, right, times FOUR. Okay, we don't have decimals. All right, so negative 9 plus 3 is negative 6. Negative 6 divided by 2 is negative 3. Negative 3 times 4, negative 12 meters. Can I leave it like that? It has to be 12 meters, yeah, downhill. Would I mark it right if you said down? Just so you know, I would not. Why? That probably seems really picky. Are down and downhill the same thing? Down is vertically downward. You're not falling through the hill. Okay? You're not rolling through it. You're rolling down it. Okay? Again, it's super picky, but vectors are vectors, and we do have to be specific. Okay, how are we feeling about that one? Okay? All right. Don't pack up, but I do want to let you know that you are staying in here for scheduled help. There's a Google Meet that I'm going to put up on the board. Administrators are going to talk about how our new late system is going to work. Okay? It's important for everybody to know what they're going to have to do should they show up for class late, which you shouldn't do. None of you should need to know this, but you all need to know. Okay? Yeah, it's kind of like that. All right. let's get that one written down and we'll try it before the bell goes.